Every drug that hasn't been discovered yet, every supply chain running at 80% efficiency, every AI model that takes months to train, these are all the same problem underneath. We are hitting the wall of what classical computers can solve. Quantum computing now isn't just about speed, it's about an entirely different way of finding answers that classical machines never will reach. And Sujoy Chakravarty, our guest today, is building QuantFluence, which is building quantum computers in India. And India might be closer to this frontier than most people realize. I'm really glad you could take out the time to do this, Sujoy. Thank you so much for doing this. And if we can start with a quick introduction from your side, and then we can move on to the questions.
Yeah, sure. Thank you. So my name is Sujoy Chakravarty, and I'm a co-founder and CEO of Confluence. So at Confluence, we're building a photonic quantum computer. We'll probably spend a lot of time talking about what we are building and why we are building it and so on. As far as my background is concerned, I'm an electronics engineer. I spend a lot of time in semiconductor, but eventually about 5 years ago, switched to quantum computing and with the goal of building a quantum computer out of India. This is my third startup, so been in this space for a while. It's been exciting, loving the journey.
Thank you so much for the introduction. Getting back to the sector understanding, and I'll share some context that I've learned over my reading, of course, is that quantum as a computing solution, one of the reasons why it exists is to solve something called the NP problems, which are essentially harder problems that cannot be solved by classical computers. Quantum, as a compute method, is focusing on optimization slash searching problems, which are harder to do using classical compute that we have at the moment. So Jay, could you also help us, give us a little bit more context as to why do we need quantum in the first place, other than, of course, these particular categories of problem?
Yeah, so I think quantum computers should be looked upon as an additional form of compute and not a replacement form of compute. A quantum computer is never going to run your spreadsheet or this meeting faster. That's absolutely not the purpose of it, right? Like you correctly pointed out, NP-hard problems are a very good case to solve here. So what that means, right, is that those kind of problems whose solution time or requirement to solve increases exponentially. So think of a problem where, for every extra variable that you add, it requires double the resources. So very soon you'll find that you're out of resources and you can no longer solve it using a classical method. Now, most other problems which these normal compute solve are more like linear problems. So if the problem size grows 10x, you require 10x more resources, right? Whereas, in this exponential kind of a thing, if the problem size grows 10x, you require 2 to the power of 10, which is a very large number, and you can no longer match it. So what a lot of these quantum algorithms do is, because of the basic properties of quantum computers, where you can hold multiple states together, these NP-hard problems or these kind of problems which have this exponential speed up curves on a quantum computer speed up linearly. So you solve that problem and all of a sudden very, very large problems which cannot be solved on normal computers can be solved on a quantum computer, right? And it also depends on algorithms. So there's a lot of algorithmic work happening, etc. So quantum computers became extremely debated or in discussion when that classic Peter Shor came up with a Shor's algorithm, right? Now, what that algorithm does, for example, is again, see the way all this encryption works on the internet today is it relies on the fact that if you take two sufficiently large prime numbers and multiply them, and if you were to publish that product out there on the web, nobody can tell you what those two prime numbers are. So it's very easy to take two large prime numbers, multiply them, but it's very, very difficult, or you should read impossible, to take a very large number and which is a product of two prime numbers and tell what those prime numbers are.
Yeah.
Right. But what Shor's algorithm showed is that, if you had a good enough quantum computer, you could get the answer to that in seconds. And if you got an answer to that in seconds, you would break all encryption on the internet. So that's just an example of what is possible using a quantum computer. So it's never going to be a replacement to an existing machine. It's going to work with existing machines to do things which cannot be done with the compute of today. That's what a quantum computer would do.
Sujoy, could you explain the different products that you have? Because from what I've read, you have you're working, of course, on the product, which is the main quantum computer, where you're trying to achieve 1,000 qubits by 2029. And parallelly, you also have some quantum inspired software using the Ising method. You also are building some sub components for quantum communication. So, could you take us through that product line and how you're thinking about it?
Sure. So the main product is, of course, the quantum computer, like you talked about, and a prototype is going to be ready by 2029. Right. So while that is ready, what we figured is that a lot of the quantum software today actually solves optimization problems. Right. And to start solving optimization problems, you don't need a full out quantum computer. You don't need what we call a gate-based machine. You could do this on a machine which runs an annealing kind of a logic or whatever. So the idea is that, if you could load an energy function onto a machine and let the machine go to the minimum, that tells you, what choice of certain variables gives you a minima. And that is the logic or the algorithm that a lot of the software guys use to solve present day problems, the optimization problems, and so on. So we do have a hardware machine to do this. It's not a software only solution. There's a hardware machine which actually does this resolving to the lowest energy state and so on. So we let the physics take over and do that part. And around that, there's a hybrid because your problem statement would not be directly compatible to be solved on the machine. So the hybrid takes it, modifies it, breaks it if needed, and then pushes the right parts onto the machine and gets the solution back and gives you an answer. And so with this, we've shown that for large enough problem sizes, which are all present in the industry, we see 8 to 20x speed up over a lot of the existing solutions or doing it the classical way. And there are also problems which cannot be solved classically, which become feasible using this machine. So that's our near-term machine. We use it to enable the solution of such problems. We don't necessarily do the software. We work with our software partners to write the application software around it, but we do the hybrid where you push a problem onto it, it gives you a solution. And so that's a near-term way of enabling quantum or quantum-inspired computing going onto the final machine.
Yeah.
The third thing that we talked about are those quantum products, right? Most of them are actually derivatives from trying to build a quantum computer. So as we build a quantum computer, we build various parts of it. And a lot of these parts have other applications in quantum or photonic or communication kind of spaces. So since those boxes are available, we also ship them to customers who are interested in it. Uh, it is a good source of revenue. It's a good source of learning for us. So that's the other product line that the company has.
At the moment, from all of your products, I would say the quantum inspired icing solution is the one which is currently being monetized and sold to customers.
Also the components. So the components is also a fairly reasonably sized business for us. So both of these are being monetized, whereas the final quantum computer is still a little way out.
Got it. And coming back to the quantum inspired solution, which is when a customer brings a routing problem to you, for example, if we take the likes of logistics routing problems that we have, can you help me understand how do they, because like you said, right, these machines don't take the problem statement independently on their own. So there will be some translation layer which converts it into a statement or like cubo format that the machine can absorb. Is your team doing that currently, or do you run it as a service independently, or how does that work?
Yeah, so there are three ways in which this works. The first way is that we have some customers who are fairly educated on this, so they just want the machine or the machine and the firmware software around it, and they run their own problems on it. So that's an easy case for us because they know exactly what they're doing. The second class of problem customers, they know that this can solve their problems, but they don't know how to convert the problem into something which can be solved on this. So there we have two approaches. Our preferred approach is to bring in a software partner who works with the customer, solves the problem, and just uses our machine in the back end. But there are some customers who prefer that we do it for them. In which case, we do have a small team which works on it. At least at the POC stage, it does that conversion. It proves to the customer that all of this works, and eventually the customer can bring a third-party team on board, or hire someone if the problem statement is large enough.
I think this is a very interesting solution, and it makes sense because although there are a bunch of optimization algorithm softwares there pre-existing, this is useful when there is an added layer of complexity that classical compute cannot solve. So this is the closest that we can get to quantum capabilities, at least at the moment. And I had a question regarding the industry, because the more that I read about how the market is in terms of how IBM is working on it, how Google is working on it, how Microsoft is working on it, they're approaching the process itself, which is the qubit creation process, from a wildly different lens. We've seen this happen before. Similar thing happened in AI. And then all of them eventually converged to something called a transformer, which came in about 2017. So the wildly different approach collapsed into one dominant architecture in AI. Do you think quantum converges similarly, or is it inherently like a CPU, GPU, TPU coexistence solution where different architectures dominate different workload?
Yeah. Uh, Interesting question, and a long question. The right answer to that is I don't know. Uh, so it's too early, too hard to predict. Uh, See, even in the early days, I don't know if you know, but GPUs were supposed to only do graphics,
Yeah.
right? And nobody gave them a lot of credence. Like there were a few companies who had GPUs, but fine, they have GPUs, they run on some application processors, and that's about it, right? Until AI came in and people realized that there's a whole class of workloads which GPUs can do. So I think things evolve. In quantum computing also they will evolve. Some types of machines may be better at something versus something else. But the universal principle that we talk about it, a universal machine where an algorithm should run on every machine. I think that calls for certain technologies to become dominant, which happened in the compute world as well, right? Like the 8086 became a dominant technology. Eventually, now ARM has come in, and similar but different technology. Right? So it's probably going to go down similar lines. But at least in the near term, I don't see this collapsing to a single technology happening until things are much more proven. There are multiple competing technologies, and uh, we figure out what's good at what and so on. So they'll exist together for a while, maybe forever. But some of them will definitely get wiped out.
Because the approaches are so widely different. But in your case, is there a baseline level of excellence or proof in terms of scaling capabilities that you test for before starting with the solution? And how does that look like before deciding that this is the solution that I will spend these couple of years on?
I think a lot of the baseline testing for scalability are thought experiments today, because you think that the following is the path to scale, and then you need to build the technology to do that. And building that technology obviously is not straightforward, because otherwise you would have had a full-blown quantum computer by now. So you're not seeing the number of qubits increasing at that rate, because while that thought experiment has been done saying if you do A, B, C, D, you can build a very large machine. And there are people submitting claims saying, the first useful quantum computers will be the size of football fields. But those are good thought experiments. But getting the technology and the engineering to that level, and making it all work, I think that's where the challenges are going to be. So everybody starts knowing that there's a path to scalability in their mind at least, and then is getting the engineering to get there. I don't think the other way is available right now, where the engineering is there and how can I scale it.
Yeah. That's completely fair. It's just that for a greenfield technology like this, it's just really important to understand how people are approaching this situation.
I think everyone looks at it the same way.
In
Even AI, I think at some point people were laughing when you said that it would be at the level that it is today.
right.
Because who's going to get the scale? How are you going to get the machines?
Yeah.
Everybody looks at it that way. Everybody has this imagination, and everybody thinks that technology will catch up, and that imagination will become true. So I think it's clear in everyone's mind that the technology needs to be scalable. How to do that today, I think there's a lot of engineering needed.
I find the field very interesting. It is so intricate, and the amount of engineering effort that goes into just understanding and making things work here at such a like a minute scale, it's really beautiful to watch, and of course, it's really beautiful to understand. Also, wanted to understand. So, what is the Quanfluence's way of approaching quantum? I know that you are using photon-based qubits as the method. Do you think that using photon based qubits sets you on a particular course or gives you a certain moat when we compare it to, say, cat qubits or superconducting or any other format?
And so obviously we believe that this is a technology which will scale.
Yeah.
Right now, it is probably much behind superconducting or ion traps.
Hmm.
But we and several other companies in the world believe that this is the technology which will scale, which is why there's investment going in here, there's a lot of work going in here, and so on. Right? And even inside of photonics, everyone follows a slightly different approach. So our approach is different from that of the other players in the market. We filed patents around that approach. And it is our belief that what we are doing addresses some of the concerns with the other photonic approaches out there. So that's the whole moat around this, right? The belief that, the ability to scale, and B, even inside photonics, doing something which addresses some of the issues with the other approaches.
One thing that I found was this natural translation. Given how optical fibers are already photon based, natural integration with that for quantum communication, I think is a very beautiful use case that falls naturally to Confluence's stack, and it's closer to Confluence than to a lot of other people because it's already photon based technology. And also, while we're at it, right? So Psi quantum, like you mentioned rightly, different people, different technologies are using different format even within photon based qubits. So they use single photon, and the more I read, the more I understand then that when you make an active choice in terms of what you're using as your qubits, there is a trade-off that needs to happen. Like for superconducting, you look at thermal noise. So they have to maintain a particular temperature, which makes the technology harder to scale with because you need to maintain a temperature. In your case, what is the error mode that you have to solve for?
Yeah, so see, all of these quantum technologies struggle with errors of maintaining state, right?
Hmm.
Uh, so the good thing about photons or photonic is that, the energy levels are such that environmental interactions are much minimized.
Yeah.
So we can do what we call room temperature compute, right? Does that mean that it solves every issue? Well, you would realize that one of the big issues here would be the actual loss in all of the stuff that the light moves around in, right? So on the chip, inside the fiber, etc., right? And when you do communication links, there are losses, but you say, I have done very well because my loss is down to 1 dB or whatever, right? Uh, the problem here is that even if we lose one photon, it is a big deal, right?
Yeah.
In the case of psi-quantum or in the case of people who are using single photon systems, if they lose a photon, they've lost their qubit, right? In our case, if we lose a photon, we've not lost the qubit because our qubit consists of multiple photons, but we've degraded the qubit. So that's basically how degradation works for us, right? For us, it's like, the losses or the imperfections which are causing uh, changes in the electric fields associated with our light modes. So those kind of losses are always there. They're the physics of the universe. So that's what we struggle to maintain. That's what our constraints are in this case.
So AI has been bullish on something called as artificial general intelligence. I compare it with super intelligence. But do you think that fault tolerant quantum is necessary to achieve ASI or super intelligence? Or is it just one accelerant among many? And is there a scenario that you think where quantum plus AI will produce something which is qualitatively very different from what either of those could produce alone, which is basically a very different kind or a different class of intelligence altogether?
Yes. So totally right. Firstly, I think this conversation you're talking of was in terms of artificial intelligence getting to AGI levels and so on, right?
Yes.
So if it does get to that level, right, the way AI operates today is a lot of learning from historical data. Right? I mean, that's AI for you. Um, so what is missing in there, right? So look at it as human beings, right? We learn a lot from historical data, but then we use our imagination, and then we need to do some calculations, right? Even in the olden days, Galileo's and Newtons of the world were doing maths and calculations, and coming up with all of this new stuff. Now, a lot of these calculations are already done, and AI is leveraging on that. But in the future, you will have to do many more calculations, which are not possible to do today, right? For example, uh, doing a weather model, right, of an entire area. You can't do it today. You're doing predictions based on, if it gets so hot, then this happens. If the wind is so much, then this happens. But with a quantum computer, you could probably do that calculation, right? And or you could calculate, let's say, an interaction between two drugs or so on and so forth. So I see a world where the quantum computer is not the intelligence source. It is the tool which an intelligence source such as AI at its AGI level uses to come up with answers which don't exist today. So instead of AI being limited to, finding out trends and analyze existing data and give you answers, it will have a tool where it can go find answers which don't exist today by calculations. So that's how quantum computers would come in and help with this entire AGI and so on and so forth. There are other uses of quantum computer which people are talking of, which is for model training and stuff like that. But leaving those aside, which is again churning a lot of data, this is like, for me, I think the best use case of these quantum computers will be that AI now has a tool wherein it can do calculations and find out new data rather than just rely on what's out there already.
No, that's a very interesting use case, and it does solve a lot of problems even within AI, like you said, neural network training and a bunch of different stuff as well. In classical computing, what we noticed was that the chip companies built the hardware, but software companies ended up capturing a lot of the margin around it, which is Microsoft, your Oracle, SAP, etc. So in quantum, you have your orchestration layer and you have, I would say, translation layer that converts normal problems to up to in a way, or like a cubo translation capabilities that converts problem into a way that a quantum computer can digest that problem, could end up being more valuable than the proton hardware itself. Do you think that trade-off, or essentially that similar kind of strategy, could come into picture where you look at quantum
Yeah.
based softwares and quantum hardware?
Yeah, I think quantum will follow the same route. So the software companies will do software and hardware companies will do hardware. About capturing value, the jury is out there. See who are the most valuable companies in the world, and they do have
Yeah,
hardware. I mean,
of
NVIDIA is
course.
basically a hardware company, and Apple basically is a hardware company. You take out their hardware, I don't know if people are going to buy them for their software only. So I think it's that synergistic relationship should continue, and software guys should do what they're good at, which is software, run it on multiple platforms, and so on and so forth. And the hardware guys should focus on improving their platform. I think it's how things have worked in the past. It's probably how things will work in the future as well.
Got
I
it.
mean, I could do software, but then I will only do software which works perfectly on my machine, and it
Hmm.
becomes like a closed ecosystem, which is fine for consumer, but I don't know whether it's good for general purpose or enterprise grade software.
No, that's fair. I just wanted to know your read on the situation. I read that National Quantum Mission has been launched, and I think about 6,000 crores have been committed through 2031. And I know Confluence has worked with and has been incubated in IIT Madras. How much of that government fund is actually flowing from your understanding and of course your interaction with the quantum mission? Do you think NQM has some constraints in terms of IP, commercialization, or international sales that affect your business model?
No, I think the NQM is structured very beautifully.
Okay.
It's a mission, so it is not a single pronged approach. They have multiple things going on. They fund universities, they fund education, and they also directly fund companies. So multi-pronged approach there, which is a good thing. Their constraints are very simple. You just need to be an Indian company, 51% Indian holding, and they are happy to work with you. They have also formed these Section 8 companies which are doing pretty good work. They can also be your customers. So a lot of good stuff happening there. The money is there. Uh, I don't see it interfering. They don't interfere with what you do. So long as you are an Indian company, they're fine, which is all good. I mean, they operate like governments are not really used to operate. So I see a lot of hope that that money will do interesting things.
It's very beautiful to see so many new initiatives and missions being launched by the government in this direction. I think it really shows support, it shows initiative, and I think that's great. The Shanti bill was passed recently, which can privatize nuclear as an energy source, and the nuclear reactor fuel rod loading ends up becoming an optimization problem. And Shanti just opened up the private nuclear investment in India explicitly to power AI, quantum, and semiconductor. So, is energy infrastructure a target for quantum solution, or is there any other synergy that you think could end up forming?
We do work with energy companies to do things like grid optimization and solve some of their complicated equational problems and stuff like that. So that goes a long way. Eventually, once quantum comes in, it's going to affect every sector. So not just the energy sector, but every other sector as well. And all this having being said, right? Eventually, I would also say that quantum is a greener technology because, all the world's hardware would probably be needed to solve a problem which a quantum computer can solve, right? So your, energy for per problem solution is massively lower when it comes to that. So that way, I think it has implications both in solving some of the problems in the energy segment as well as in reducing the consumption of energy while doing compute.
Absolutely. Pushing back a little here from my understanding. And of course, this could be a very, very naive question, but do you think the problem that can't be solved now is worth solving in the future? I see that a lot of optimization problems are unsolvable due to the nature of compute and the scale of the problem itself. But are those problems worth solving? I feel like we solve a problem and then we create another problem, which is, we have your encrypt now decrypt later. And for that, now we'll have to look at quantum safe systems, right? So it's like solving a problem but creating another problem, and it just sort of becomes a loop.
No, no, I think every problem is worth solving. And yeah, I'll give you an example, right? If you could cut down the time to get a drug to market from the 10 odd years that it takes today to a year, is it worth solving that problem? And the answer probably is yes, right? So I think all the problems which open up because of this are worth solving for humankind, right? It might go and solve some problems which we don't care about, but in general, I think material discovery. If you can find a material to build far more fuel efficient aircraft faster,
Yeah.
Today, that process takes years and years and years, right? If you could find that material in a few months, imagine the amount of energy you solve for the world, right?
Yeah.
Or energy cost, etc. So definitely worth solving.
Got it. No, of course. Thank you. Thank you for your take on this. I actually just wanted to understand that. Yeah, so this is it from my side, Sujoy. Thank you so much for doing this. And if you have any questions for me, happy to answer that. I hope this podcast encourages a lot of people to follow and closely follow what is happening in the sector, because it is so important, and I cannot underscore the importance of quantum as a technology.
Yeah, thank you. Thank you for having me here. And I encourage everyone to keep up to date with what's happening. You can follow us, come to our website, drop us a note. We are always happy to answer questions and engage with everyone. And looking forward to all the support which everyone can provide as we go ahead in this journey. We really want to make it happen. Thank you.
Thanks, so,